Today on Quickly Quantum, Caltech says a team of its researchers just used a quantum simulator to directly measure physics predicted 40 years ago and never actually observed until now. So is that the win this industry's been promising, or a reminder of how far useful quantum computing still has to go? Before that, in the headlines, Rigetti splits its engineering organization to chase a hard-fidelity target. A hardware security module claims a first in post-quantum cryptography certification, and a hardware wallet maker says quantum-safe signatures already run on the device you might own right now. Welcome back to Quickly Quantum, your daily brief on the quantum frontier. It's Friday, August 21st, 2026. There's a genuine physics claim today that's got me thinking harder than usual. Let's get into it. Rigetti Computing split its engineering department in two this week, and it's the kind of internal reshuffle that actually tells you something. The superconducting qubit company created a brand new systems delivery organization, basically the team that builds, ships, and supports the physical machines customers install on their own premises, under a new chief operating officer, David Rivas. Meanwhile, Andrew Bestwick, promoted from his role running quantum systems, becomes chief technology officer, in sole charge of the actual processor research. So why split the org now? Rigetti's betting that separating delivery logistics from the science lets the hardware team focus on hitting a stated target of 99.5% median 2-qubit gate fidelity on its Cepheus 1 108Q system, built by tiling 12 9-qubit chiplets together. Now, that fidelity number is still a roadmap goal, not something you can point to as achieved yet. But when we checked in on Rigetti's books earlier this month, the story was $5.1 million in quarterly revenue against a $52.6 million net loss. So building a structure specifically around delivering and supporting hardware to paying on-premises customers, from national labs to quantum centers, is exactly the kind of move you'd expect from a company that needs that revenue line to start moving. Here's a milestone from the unglamorous side of quantum security. Crypto4a says its QASM cryptographic module just became the first quantum-safe hardware security module to hit FIPS 140-3 Level 3, the U.S. government's higher assurance certification tier, the one that demands real physical tamper resistance, not just software correctness. Why does that particular tier matter to you? Because governments and banks have been waiting for exactly this kind of independently validated hardware before they'll deploy post-quantum cryptography at scale, and the module supports every algorithm NIST has standardized so far. Crypto4a's co-founder and CEO, Bruno Couillard, put the urgency bluntly. Quote, "Quantum computing is moving at an ever faster pace towards being able to hack into today's networks faster than you can snap your fingers, and most of the systems we rely on aren't ready for it." End quote. Now, that's a vendor talking about its own product, and world-first claims in certification announcements are exactly the kind of thing worth checking against NIST's own validated modules list rather than taking the press release at face value. But the underlying need is real. This higher assurance tier is genuinely a bar most quantum-safe hardware hasn't cleared yet. If you own a hardware wallet and worry about the day quantum computers can crack today's encryption, Blockstream says its research team just ran a demo aimed squarely at that fear. The company's own account at Blockstream Jade posted on X that its researchers implemented SLH-DSA, the hash-based NIST-standardized post-quantum signature scheme, on 4 popular hardware wallets, including its own Jade Plus, claiming all 4 signed successfully with a worst-case signing time of about 2 minutes. The post credits at Ol Kurbatov and Dmitry Kurbatov for leading the work, reviewed by @Nickler, and frames it as a direct answer to a standing worry in crypto custody circles, that post-quantum signatures are simply too heavy for the low-power chips inside the wallet you probably already own. Now, this is the company's own demo of its own devices, corroborated only by that single post. We haven't independently confirmed the signing time numbers, the wallet list, or what firmware changes it would actually take to ship this, so treat every number in that claim as Blockstream's own account until someone outside the company checks it. But a working demonstration on shipped hardware beats a white paper, and a claimed 2 minutes worst case, according to Blockstream, turns what used to sound like a hardware limitation into an engineering question, if it holds up. Now, a quick one from the physics side of X. An account called At Quantum Boom Now posted a digest describing a paper it calls Recovering Coherent Errors, claiming the technique improves quantum error detection precision without needing extra hardware and boosts gate fidelity at a fixed cost. The post itself cuts off mid-sentence, so that's about as far as the details go, and we can't independently verify the paper, its authors, or where it was published from this alone. So why give a partial tweet any airtime at all? Because gate fidelity, basically the batting average of a quantum operation, how often it does exactly what you told it to instead of drifting into an error you have to correct for later, is the kind of incremental number that quietly compounds across this whole industry, even when we can't yet trace a specific claim back to a named lab or a named journal. Any technique that boosts that number without new hardware is worth a second look, once somebody can actually verify what's in the paper. For today, file this one under interesting if true, rather than settled science. One more date for the calendar. The Quantum Insider reports that Bleichroeder Acquisition Corp. II, the SPAC trying to take Pasqal public, has set its shareholder vote for August 25th, with the outlet saying that vote follows the SEC declaring the company's joint registration statement effective. We haven't independently confirmed that beyond the one outlet's reporting. Pasqal is one of Europe's leading neutral atom quantum computing companies, and a yes vote would make it the latest hardware firm to go public this way, following the paths IonQ, Rigetti, and D-Wave already walked, though the deal remains subject to shareholder approval and the usual closing conditions that can still delay or sink a SPAC merger even after a date's on the books. Now, Pasqal's own account, at Pasqal Quantum, was also on X this week, noting that its work on AI-assisted agentic tools for quantum programming got picked up by Nature under a headline that made me do a double take. AI tool lets researchers vibe code in the quantum realm. Timing you can't buy, right as the company heads into its public market vote. And speaking of neutral atoms, that's the exact same hardware family, laser-trapped atoms held in place with what's called optical tweezers that a Caltech team just used for a physics result that's got the field talking. That's our main story today. And I'm calling it the confirmation problem. Caltech says its team just used a quantum simulator to measure, for the first time, something physicists have believed for 40 years. So what does it mean when a machine's clearest win is grading homework correctly instead of teaching you something new? Here's what the team and Caltech's own newsroom describe. A team led out of Caltech, combining the experimental lab of Manuel Endres with a theory group of Jason Alicea, plus theorists from Université Paris-Saclay and the Technical University of Munich, says it built a chain of up to 35 strontium atoms held in place with laser tweezers and pushed them into what's called the Rydberg blockade regime, a state where neighboring atoms interact so strongly that exciting one blocks its neighbor from also being excited. Tuning the lasers just right, according to the team, puts that chain of atoms exactly at a quantum phase transition, the point where a system flips between two very different behaviors, the same basic idea as water turning to steam, except here it's happening in the quantum realm at temperatures near absolute zero. Now, 40 years ago, physicist John Cardy worked out a mathematical framework called conformal field theory. Think of it as the rule book for how energy levels behave, universally, right at one of these critical points. His theory predicted a very specific pattern, a set of low-energy rungs, like a ladder, whose spacing should follow the exact same ratios no matter what specific material you're looking at, as long as it's at that same kind of transition. This is the same broad mathematical territory that shows up in the ADS-CFT correspondence, a deep conjecture linking gravity and quantum theory used in the most theoretical corners of high-energy physics. So this experiment, if it holds up, probes something with reach well beyond one lab bench. That prediction sat there for 4 decades, mathematically elegant, and Caltech says it had never been directly measured in a real physical system until this result. The team says it pulled this off using a technique it calls many-body modulation spectroscopy, gently jiggling the laser controlling the whole atom chain at different frequencies and watching how the system responded. Sweep through enough frequencies and you can map out the actual energy levels. And according to the paper, When the team did that across chains of up to 35 atoms, the rungs came out exactly where Carty's Ising conformal field theory said they'd be. The team also says it confirmed the more exotic tricritical version of the theory, and that by individually controlling atoms at the edges of the chain, it tuned between 3 different boundary conditions and watched the spectrum shift the way the theory predicted. According to Caltech's own announcement, the work is published in Nature and backed by the Department of Energy's Quantum Systems Accelerator and Quantum Science Center, the National Science Foundation's Institute for Quantum Information and Matter at Caltech, DARPA, and the Air Force Office of Scientific Research. Real institutional weight behind a piece of physics Caltech is calling genuinely careful. And here's the detail that should matter to you even if you don't follow quantum hardware closely. The machine here is strontium atoms held in optical tweezers using Rydberg interactions, the exact same broad architecture that companies like Q-Era and Pasqal, the neutral atom company we just mentioned heading toward its own public listing, are selling right now as a path to scalable, commercial quantum computing. So if this result holds up under further scrutiny, it lends real scientific credibility to that whole hardware family, even though, and this is the catch worth sitting with, what's being claimed here is a measurement of physics researchers already trusted, not a computation classical computers couldn't also do. So how do we square this? If Caltech's account is accurate, this is genuinely elegant, rigorous physics, a 40-year-old theoretical prediction, independently verified using a totally different kind of machine than anyone imagined when Carty wrote it down. Nature doesn't typically publish sloppy work, and having theorists from 3 different institutions checking the numbers, according to the team, means this result got scrutinized hard before it saw daylight. But here's the tension worth sitting with instead of smoothing over. What's being claimed is a measurement of one-dimensional conformal field theory that physicists already believed, calculated with pen and paper decades before this experiment existed, and confirmed, the team says, on a system small enough, 35 atoms, that you could, in principle, still simulate it slowly on a classical computer. That's the honest skeptic's case, and it's not really contested. The Caltech team's own stated next step is scaling this technique up to 2-dimensional grids of atoms, where conformal field theory is far less understood, and a classical computer genuinely couldn't keep up. That 2-dimensional leap is where an actual quantum advantage claim would live. This experiment isn't that yet. So what does that mean for the phrase, useful quantum computing, which every hardware company on Earth is currently trying to claim for itself? I think this result, if it holds up, is a pretty clean illustration of where the field actually stands, and it's more honest than the marketing version of that question usually allows. Quantum simulators, devices built to mimic one specific physical system rather than run arbitrary programs, have quietly become the most reliable near-term output this industry can point to. Not breaking encryption, not beating a supercomputer at a sampling stunt built specifically to be hard for classical machines, but doing what Caltech describes as real physics you couldn't easily do any other way. Watching a decades-old theoretical prediction actually play out, atom by atom, in real time. That's a genuine capability, if the claim checks out. It's just a scientific instrument capability, not a computational advantage one, and those two things get blurred together constantly in this industry's press releases. Now, the other thing worth saying plainly, this same hardware family, neutral atoms in optical tweezers, is exactly what Q-Era and Pasqal are trying to sell into enterprise and government contracts right now. A Caltech physics paper doesn't directly validate anyone's commercial roadmap, but it does suggest the underlying control, the precision, the individual atom addressing, the ability to tune boundary conditions atom by atom, works well enough, if Caltech's account holds, to do genuinely hard, genuinely precise science. That's not nothing, and it's the kind of quiet technical maturity that tends to show up in earnings calls 18 months before anyone outside the field notices it happened. Time for the hype check. I'm calling this one a 6. The physics, as Caltech and the Nature paper describe it, is clean, and the corroboration across outlets, Nature, Caltech's own newsroom, and HPC Wire all covering the same result, is about as strong as this show sees on any given day. But the gap between we confirmed known theory and useful quantum computing is exactly the gap this industry needs you to stop noticing, and I'm not going to help with that today. Here's the marker I'll actually be watching. If that two-dimensional version of this experiment gets run on a chain too large to simulate classically, and the numbers still line up with theory, that's the day this stops being a validation story and starts being an advantage story. That's the show for today. If watching physicists say they've finally nailed a 40-year-old prediction is the kind of story you want waiting in your feed tomorrow, go ahead and follow Quickly Quantum wherever you're listening. That way, you won't miss the day this technique gets tried on a system too big to check by hand. This has been Quickly Quantum, an AI-voiced podcast created and built by a real human using today's cutting-edge technology. Nothing you heard on this show is financial advice. I'm Brian Lampert, and I'll catch you all tomorrow. Take care.